Hey everyone, and welcome to today's Explainer. Go ahead and grab a seat, settle in, because today we are tackling something absolutely crucial. We're mastering EtherChannel concepts and configuration strategies. Look, whether you're a seasoned network engineer just brushing up on your routing or a student prepping for that next big certification exam, mastering Layer 2 and Layer 3 bundling is a total must-have skill in your engineering toolkit. We're going to break this down step by step so you can confidently deploy it in your own real-world environments.
All right, here's our syllabus for the session. We'll start with the network congestion problem, then define what EtherChannel actually is. After that, we'll hit the Layer 2 config steps, the Layer 3 config steps, talk about consistency and verification, and wrap up with the core benefits. Okay, let's dive into this.
Section 1. The network congestion problem. You know, practically every great technology out there was invented to solve a specific painful problem. And in our world of networking, one of the most painful issues you can face is congestion. So let's set up a design scenario that honestly might hit a little too close to home for some of you.
I really want you to think about this central question for a second. How do we actually prevent bottlenecks when hundreds of users connect all at the exact same time? Just picture it. Monday morning, 9 a.m. Everyone logs in, they open their emails, fire up those heavy video calls, and suddenly the network just crawls. Your help desk is lighting up like a Christmas tree. What's the physical limitation causing this? And more importantly, how do we fix it before our users even notice a blip?
Well, here's the specific scenario. Imagine you've got a building with 3 access switches, and each one of those is serving hundreds of users. All 3 of these access switches connect upstream to a single central distribution switch. Now, if each access switch only has a single uplink cable to the distribution layer, you've created a massive funnel. Literally hundreds of users are trying to squeeze their data through one physical wire at the same time. Now, you might be thinking, hey, just buy a fatter, faster cable. But constantly ripping out and replacing cables for higher speeds, that gets insanely expensive and it's just inefficient. We need a much smarter way to handle this bottleneck.
Which brings us perfectly to Section 2, what is EtherChannel? This is where we get to introduce the technological hero of today's lesson, because solving that exact bottleneck is exactly what EtherChannel was built for. By definition, EtherChannel is simply the process of grouping multiple physical interfaces into one single logical port channel interface. So instead of relying on just one uplink cable from our access switch to our distribution switch, we can plug in 2 or 4 or even up to 8 physical links and bundle them all together. We literally configure the switch software to treat that whole bundle of cables as if it were just one giant logical pipe.
Now, what's really interesting about this slide is the concept of one. You see, Spanning Tree Protocol, or STP, is designed to prevent network loops by blocking redundant physical paths, right? Normally, if you plug 2 cables between the same 2 switches, STP kind of freaks out and blocks one of them to prevent a loop. But with EtherChannel, STP treats this entire massive bundle of cables as just one single logical link. So 0 ports get blocked, and you actually get to use all the bandwidth you paid for.
Let's map out how this fits into your overall network hierarchy. As you move up from the access layer to the core, you generally see 2 main flavors of EtherChannel. When you're connecting your access switches to your distribution switches, you're typically building a Layer 2 trunk EtherChannel. That means you're dealing with STP and VLANs. But as you move higher up the chain, say from distribution to your core network, you're usually building a Layer 3 routed EtherChannel, and that type relies on IP addresses and routing protocols like OSPF or EIGRP.
All right, class, Section 3, Layer 2 configuration steps. It's time for some practical lab work. Let's actually look at the configuration steps to build that Layer 2 uplink between our access and distribution switches.
To build a Layer 2 Etherchannel, you're going to follow this precise logical flow. First up, you select the physical interfaces you want to bundle. Let's say gigabit 1/0/1 and 1/0/2. Second, you configure them as switch ports and set them to trunk mode so they can carry multiple VLANs. Third, you assign them to a channel group. And you've got to pick a negotiation mode here, like active if you're using the industry standard LACP, desirable for Cisco's PAgP, or on if you just want to force it statically. Once you do that, the switch magically creates a brand new virtual interface called a port channel. Step 4 is absolutely critical, guys. You must configure that new logical port channel interface exactly like a normal switch port, applying the exact same trunking and VLAN access settings as the physical ones.
Moving right along to Section 4, Layer 3 configuration steps. Let's shift our focus and step 1 tier higher in our network topology. How does routing change things when we connect our distribution switch to our core switch?
Well, before we type any commands, let's look at this comparison because it brilliantly illustrates the fundamental difference in the syntax. Notice the contrast here. For Layer 2, we lean heavily on the switch port command, dealing entirely with MAC addresses, VLANs, and trunking. But for Layer 3, we literally have to tell the switch, hey, stop acting like a simple switch on these ports. We do that using the no switch port command. That strips away all the VLAN tagging and turns those physical interfaces into pure routed Layer 3 ports that can take IP addresses and subnets.
So keeping that in mind, our Layer 3 lab steps look like this. Step 1. Select the physical interfaces. Step 2. Immediately enter that no switch port command on those physical ports. Step 3. Assign them to a channel group, again picking a mode like active. At this point, the switch creates your logical port channel interface. Finally, Step 4. You dive into that port channel interface, issue no switch port again just to be totally safe, and then assign your IP address in subnet mask. Boom! You've now got a massive bundled routed link fully ready to participate in OSPF or EIGRP routing.
Okay, Section 5. Consistency and verification. Now, I know you guys, and I know that in the real world, things don't always work perfectly on the very first try. So let's get into the troubleshooting phase. What happens when configs don't match?
Listen, if you take away nothing else from today's explainer, please memorize this golden rule. Consistency is non-negotiable. Every single member interface in your bundle must match exactly in these 4 specific areas: speed, duplex, layer mode, meaning no mixing Layer 2 and Layer 3, and VLAN configuration. If there's a mismatch anywhere in there, the channel group will simply fail to form. In fact, mixing Layer 2 and Layer 3 settings, that is one of the most common errors engineers run into out in the field. The switch just flat out rejects it.
So, to verify your work and troubleshoot those golden rule mismatches, you need your toolkit. First up, Show EtherChannel Summary. This one is your best friend. It tells you instantly if the group is up and exactly which ports bundled successfully. Second, Show Interfaces Port Channel lets you check the status of that newly created logical interface. And finally, Show EtherChannel Load Balance lets you peek under the hood to see exactly how the switch is distributing your traffic across the physical wires.
And speaking of load balancing, I'll read this quote really quick. Load balancing is flow-based, not packet-based, so a single flow will always use one physical link, but multiple flows are spread across the bundle. So the crucial point is this, and it's a super common misconception. If you transfer one massive 50 gigabyte file, it's not going to be chopped up and sent equally across all 4 cables in your bundle. Nope, it's going to pick one physical link and max it out. The real magic of EtherChannel happens when you have hundreds of different users generating multiple different flows. That is when traffic beautifully spreads out across the whole bundle.
Section 6. Core Benefits of EtherChannel. To wrap up today's lecture, let's zoom back out to our original scenario with those 3 bottlenecked access switches and quickly summarize the big wins here.
By deploying this tech, we snagged 4 massive benefits. First, bandwidth aggregation. We effectively doubled or quadrupled the capacity for our access switches without having to buy new, expensive equipment. Second, seamless redundancy. If one of those physical cables gets accidentally unplugged or chewed up by a rat, traffic seamlessly continues over the remaining links. Nobody drops their Zoom call. Third, simplified STP. We basically tricked Spanning Tree into seeing one logical link, so it stopped blocking our redundant ports. And fourth, scalability. If we need more bandwidth next year, it's incredibly easy to just plug in another cable and add it to the existing bundle. So, class is about dismissed, but I want to leave you with this question to chew on. Take a look at your own network architectures right now. Where is your biggest bottleneck? And when you finally go to fix it, will you utilize a Layer 2 trunk or a Layer 3 rotted Ether channel? Think about your hierarchy, remember the golden rule, and go build a faster network. Thanks so much for joining me for this explainer. Keep learning, and I'll catch you guys next time.